think this thing is broken.
Oh, okay. Better now?
I mean, it works, but
Okay. Do it need some gray duct tape?
yeah.
Okay. Gray duct tape fixes everything. Okay. So, if you're planning ahead, the test over this thermodynamic stuff and buoyancy will be on Thursday of next week. Okay? Then we'll review on Friday, and then the written final is going to be the following Monday. And then they're going to have a 3-day lab final, Tuesday, Wednesday, Thursday. Lab final will be due at the end of the day on Thursday, and then Friday we'll kick back and have a good lunch and celebrate the passing of the torch. So,
Yes.
so if you're going to plan ahead, you have one more big test over this thermodynamic stuff, and then the lab or the written final over everything from day one, and then the 3-day lab. So, bless you. Okay. All right. So, yesterday we talked about these calculations of Q, and Q is the amount of energy that's in the system. So, here's the question. When do you use these two with like this one that has this latent heat of fusion, and this is this latent heat of vaporization? So when do you use these two versus when do you use the top equation?
Those two are used for state, like a change of state.
Yeah. So this is going to be some phase change, right? So this is going to be like when you're going from like a solid into a liquid, which would be this latent heat of fusion. So like if I gave Shively his lab final and said, okay, hey, your lab final is to melt a piece of ice. Oh, okay, right, no worries. So if you're just talking about that process of melting ice, you're going to use the latent heat of fusion. Now, if I went to Logan and I said, hey, Logan, your job is to take water and freeze it, here's the cool thing about it. The amount of energy that you have to remove is the same amount of energy that Shively has to put in to make it melt. Okay, so the same door swings both sides. Now, on your data sheet, don't memorize this now. So your latent heat of fusion is like 3.33 times 10 to the 5th joules per kilogram. And your latent heat of vaporization, so this is going to be like boiling or condensing water. Okay, so this is going to be, I think that's 22.2. Same thing, times 10 to the 6th joules per kilogram. Now, here's the deal. Notice that it takes a lot more energy to boil water by basically an order of magnitude of 10. It takes a lot more energy to boil water than it does to melt ice. Okay? So, just keep that in mind. So, now, here's the question. Why isn't there like a degree Celsius in here like there is on specific heat? So specific heat values are joules per kilogram degrees Celsius. So why does this have a Celsius on it and these two don't?
Because there's no temperature change.
There's no temperature change. But here's what's important. Where is that? But that energy has to go to do something. So what's that energy doing when you're talking about latent heat of fusion or latent heat of vaporization?
Breaking the bonds.
So if you're melting something, you're putting energy in and you're breaking bonds. So here's the universal truth, no matter where you're at. So here's this chunk of ice. If you're going to melt it, at the end of the day, you've got to dump energy into it. And that energy is going to go to break bonds. Now, when you form new bonds, that energy is going to get released. So this is why when you take water and you're going to try and freeze it, you've got to extract that energy out of it. Okay? So that in forming bonds, you have to give that energy a place to go. And that's why when you're taking water and you're trying to change it into ice, you put it in a freezer. Because of the fact that you're extracting that energy out so that bonds can form. If you want to melt ice, you're going to reverse the process. You're going to put it on a stove. And that stove is going to provide the energy that's going to go in, and it's going to break those bonds because energy has to go in to break the bonds. So if there's any temperature change at all, you use M delta T C sub B. If it's any type of phase change, and there's only only ones you're going to have to worry about is for ice and water. So if it's ice, you're using that latent heat of fusion. If it's ice or boiling water, it's this latent heat of vaporization. Cool with that? Grand? Okay. Now, Max, stop that. So these are just like
Player.
All right, kids. So
Not-
what we got to go through is, especially on the back side of the selection notes that I just gave you, okay? And we'll talk about everything else, but here's the basic idea. Is that the main lecture today is going to come off of what's known as a pressure volume graph. So the good news is this is the last graph we will ever talk about in this class, okay? Of all the graphs we talked about, this is the last and final shot.
Is it bad?
Yeah.
Is that really confusing?
Huh?
The X value,
What do you mean?
is that 0.03?
Yeah?
Yeah.
Isn't that what 0.01 is?
No,
You-
this
no.
is volume, 0.01, 0.02,
But your
and
point-
0.03.
What are
Your
you
point
talking about?
up there at 1.2, it says 0.03.
Oh, okay, my bad.
That's what he was talking about.
Okay, I thought you were talking about that.
No,
Nigga, that is crooked bird.
Let's
no,
go
I
next.
didn't mean to like that.
No, we're good, we're good. That's what it should be. Okay, so what we're gonna do is we're gonna look at 3 different processes. And the good news is, we're gonna start with the most difficult and complex of the 3 processes. And then we're gonna end up with the simplest one. Okay, so we're gonna get the hardest one out of the way. So, first off, let's talk about the graph itself. You got pressure on the y-axis, and you've got volume on the x-axis. So all this is a coordinate pair. So what we're doing is we're plotting pressure versus volume. So that first point up there is 0.01 cubic meters, which is, you know, this is about, that isn't a huge volume. It's 0.01 cubic meters, okay? It isn't a huge thing. And we got a pressure of 1.2 times 10 to the 5th newtons per square meter, which is a little bit higher than what you're used to, okay? We're at standard atmospheric pressure. 1 atmosphere is about 1.0 times 10 to the 5th newtons per square meter. So this pressure is a little bit higher than normal. And in this system, in this container, we're going to have 0.1 moles of some gas, carbon dioxide, nitrogen, pick one, I don't care. So here's the drill. What we're going to do is we're going to look at taking this thing through different processes. Now, on the back side of these lecture notes, you'll notice that there's 3 processes: isobaric, isothermic, and then isometric. Sometimes isometric is called isovolumetric. So let's talk about what iso means. So when you all were in your freshman general science class, did you all ever take a map and draw lines that connected the points of equal pressure on a map? Seriously?
I think that was the hurricane, the earthquakes, the waves, that's what we
Yeah,
did.
that's what that one thing that measures.
We did the P waves and
Did y'all not do weather?
I don't think
We
so.
Oh, really?
did weather, but not
Serious?
much.
No, we did. I just it was really small unit kind of.
Okay.
thing.
Yeah.
All right, so lines of
Flavors
equal
yourself.
pressure on a map are called isotherms. Lines of equal pressure are called isobars. So if you look at a weather map and you see isobars that are really, really bunched close together, that means that that's generally an area of really, really strong winds because you have a huge pressure gradient. Lines of equal temperature are isotherms. So iso means similar. So what we're going to look at is 3 different processes. The first one we're going to look at is isobaric, meaning that we're going to keep the same pressure. The second one we're going to look at is going to be isothermal, and then the third one we're going to look at is isometric. Okay, so we're going to go with the most complex system first, and then we're going to go end up with the simplest one. Because if you can understand the most complex first, then everything else becomes simple. Okay? So here's what's unique about a pressure volume graph. Even though you're plotting 2 dimensions, pressure and volume, there's actually a third thing that you can determine if you know the number of moles in the gas. So if I know I've got a pressure, a volume, and a number of moles, what else can I find?
Temperature.
I can find temperature. So here's what's cool about this graph. It's almost like a 3-dimensional graph in the sense that you can always find pressure, you can always find temperature, or pressure and volume, and then out of that, as long as you know the number of moles, you can find what the temperature is going to be. So here's what we've got. So if you look at what Max talked about, we know that PV equals nRT. I know my pressure, I know my volume, and I know my number of moles. I know my ideal gas law constant, so I can find the temperature. So, Logan, how am I gonna get temperature by itself?
Divide by NR.
Yeah, so I got pressure, volume divided by NR equals my temperature. So I got my pressure, which is 1.2 times 10 to the 5th. So somebody get a calculator out. Harry, get ready to verify what somebody calculate.
Do you want me to verify marriage?
Square meter. I got a volume of 0.01 cubic meters, and then I've got N, which is 0.1 moles. And then I've got my R, 8.314 joules per mole Kelvin. You go through all this rigmarole, you get Kelvin. What do you get?
1443.
1443.
Thank you, Mary.
Are we good, Mary?
We're good.
Fantastic. Now, that's pretty warm. Even if you subtract 273 from it, you're over still over 1,000 degrees Celsius. So it's pretty warm, okay? But remember, this is, just because you have a high temperature doesn't mean that you have a lot of heat. Like, for example, the warmest layer by temperature in our atmosphere is the highest level in the atmosphere. That's the highest temperature. But you'll freeze to death out there. So you have particles that are moving really, really fast, but you don't have a lot of particles. So just because you have a high temperature doesn't necessarily mean that, oh, this is going to be really, really hot. It just means that the individual particles are moving really, really fast. So here's the point. So I got a pressure, I got a volume. From that, I can always find a temperature. So here's what we're going to do. Let me do a little bit of erasing here so I'm not drawing over everything. So here are the three numbers that we need. This volume, that pressure, that temperature. So here's what we're going to do. So we're going to take this gas, which is this volume and this pressure, and we're going to bring this line across like this, and we're going to end up out here at 0.03 cubic meters and 1.2 times 10 to the 5th newtons per square meter. Okay? Now, before we do any calculations, you have to understand conceptually what's taking place. So I'm going to model this with this syringe, okay? So I've got a certain volume right here, okay, 0.01, whatever it is. So here's what's going to be important. I'm going to go from 0.01 to 0.03, so I'm going to triple the volume, okay? So what would I physically have to do to this syringe to model this? What would I do?
Pull it.
I'm going to pull this out, right? So that's going to go from like 5 up to 15. Okay, I'm going to increase that volume. Now, am I going to change the number of moles of gas in the system?
No.
No. But here's what I want you to think about. Even though I'm increasing the volume, my pressure is going to stay the same. Now, here's what I want you to think through. You have to realize what's creating pressure. So what's creating pressure on an atomic level are these particles slamming against this pressure sensor. So imagine this is a room full of Timmies, okay? This is going to be important. We're going to start with Timmies. We'll get to Dash later, okay? These are normal Timmies. Squirrely, they're second graders, but they're Timmies nonetheless. So this is like a room full of Timmies in a normal situation. Now, I'm going to increase the volume of the room. Okay, I'm going to increase the volume of the room. So what's going to happen to the number of collisions with the walls? Should decrease. So if I just increase the volume and hold everything else constant, what do you think should happen to the pressure?
It should decrease.
It should decrease because the room's getting bigger, right? You're not going to have a same number of collisions. So here's my question. So imagine that you have a room full of Timmies. We're going to triple the size of the room, but our pressure sensor is still going to read the same value. So what has to happen to the energy of each collision? It's got to go up. So I'm increasing the volume, but I'm keeping the same pressure. So what has to happen? All of those Timmies have to turn into Dash, right? So now you got these particles on steroids going, okay? Now, what do we have to give the Timmies to make this happen?
Energy.
Energy. We got to give them Skittles, right? Okay. We got to dump a bunch of energy into the system to maintain this same set of conditions. So eventually, we're going to calculate this new temperature. So is this new temperature over here going to be bigger or smaller than 1443?
Bigger.
It's got to be bigger. Here's what's important. So if you can conceptualize what's happening in here, going, oh, right, okay, got Timmy's, small room. Room gets bigger, same pressure, Timmy goes on Skittles, okay? So, and remember, temperature is a measure of the kinetic energy of the particles. So, I'm not changing the number of particles. I've got the same number of Timmys. But now we're going to go from Timmys into dashes, okay? Now, this is a children's book I'd love to write, although I don't know if I could. But you're like, wow, now we've got dashes. It's just bouncing off the walls. So, if you can animate that, but... So, they go, oh, that's child cruelty. Yes, it is. Okay. So, I'm just saying. All right, so, this thing's going to go across. Can I find the new temperature?
Yes.
Yes, because I got the pressure and I've got the...
Volume.
And so I can find the temperature. So we're going to repeat that process. And we're going to, oh, right. So I'm going to have the pressure times the volume. So I got these two numbers, and then divide that by the same NR. So this times this divided by, my number of moles was still 0.10 moles. So what do you get? Should get, I think, 4,000 and something. Because basically, all you have to do is just basically take this times 3.
You need to divide that by 0.1 times 8.3. Yeah, but that's 4,330. 4,330.
That sounds right. 42. 4,330 Kelvin.
Yeah.
Okay, everybody cool with this?
Wait, what did we divide by? Sorry.
So we took PV divided by NR is going to equal temperature. So we took these two numbers here on the pressure volume, and then divided that by the moles times 8.314. 100.
T1 over T1?
You can do that too. Yeah. You can do that too. It's the same thing because number of moles stays the same thing. Or you could just look at this and go, oh, I'm going to triple the volume. Everything stays the same. So the temperature has to triple as well. There's any number of ways you can do it. But here's the point. I ended up with 4,330 Kelvin. So the temperature went up. So we went from Timmy's into dashes. Okay? We're going 3 times as fast. So this is how we can maintain the same pressure because the particles are going a lot faster. Now I want you to visualize this. Okay? So we had this at 5, right? We're triple that. We're going to go up to 15, right? Volume's gone up. Temperature's gone up. So here's the question. What would you physically do to the syringe to make that happen? What would you have to do?
Close the hole.
Now, well, I know that it's assumed that that's closed. Okay, so we're going from 5 up to, and that's going to be closed so that way we keep the same number of particles in the system. But what would you do? Let me give you a hint. You're either going to dump energy into it by putting it like in a hot water bath, or you're going to take energy out of it by putting it in a freezer.
But energy.
You're going to dump energy into it, okay? Because something has to add energy to the system. These particles aren't going to speed up on their own. So when you see a higher temperature, that means you have to dump energy into the system. So I would have to physically heat this thing up, put it in a microwave, put it in a hot water bath, okay? Do something with it. First block said, breathe on it. It's like, weird. Okay. All right. So we got this set up. So at this point, I've got 2 different points. So now, here's going to be the next thing. On the back side of this, of your lecture notes, okay, and it's on your equation sheets too, there's a couple of big ideas. One is delta U equals Q plus W. Delta U also equals 3/2 NR delta T. Work equals negative P delta V, and work equals NRT natural log VI over V. Okay? So these are the four big equations that you're going to need. I've got them on there. This one isn't on your equation sheet, but if you need it for the test, I will give you this equation. Okay, you just have to know how to use it. Now, let's talk about what these things are. So I've got volumes, I've got temperatures, I've got pressures, delta U's. Let me explain what delta U is. Delta U is the total amount of energy in the system that can come from a couple of different sources. It can come from work, okay? This is just your normal work, force times distance, okay? Q is the thermal energy going in and out. So you have two things. You have thermal energy going out, and you have work, okay? So that's what these two are going to add up to. Now, the delta U is the total amount of energy in the system. So here's what you cannot measure. If you look at what you can buy to measure systems, measure things in a thermodynamic system, there is no such thing as a delta U probe. You cannot measure it. It isn't like, oh, I want to measure delta U. I'll stick the probe in. Oh, delta U is 5,000 joules. Okay? We talk about it. It's important, but you cannot directly measure it. So these quantities that are up here, what do you think we can physically measure?
The temperature.
Yeah, temperature. Okay, hey, we can measure the temperature of the system. Okay, that's kind of a home run deal. What else?
Pressure.
Pressure. Okay, hook it up to a pressure sensor. Okay. Guessing y'all might have done that in Chem 1. Okay. What else?
Number of moles.
Number of moles, right? Okay. That's tougher to measure. That's usually a given quantity. Because it isn't like, oh, we can make here's a mole sensor, and we'll put that in and go, oh, there's 0.5 moles of gas inside the container.
Volume.
But certainly volume, okay? Because we can look and say, hey, what's the volume of the cylinder? So here's what's important conceptually, is that we measure what's happening on a macroscopic level. We measure temperature and how that fluctuates. We look at volume, we look at pressure. And from these macroscopic ideas, we figure out what's happening on an atomic level, okay? So we can't observe like an individual oxygen molecule. It isn't like, it isn't like we can put like a GPS tracking unit on an individual oxygen molecule and track it as it goes through this system, okay? Can't, not even on a dare, okay? So, but what we do is we look at, on average, what's happening with these systems. So, this delta U is going to be the total system. Now, here's what's going to be important. There's two ways that you can calculate delta U. You can add the energy that's flowing in or out, and this is what Q is. Q is the amount of energy flowing in and out. Work is going to be work. And so these two values added together gets you delta U. The other way that you can calculate delta U is that it's 3/2 nR delta T. The 3/2 comes from a statistical viewpoint. So don't worry about that for now. Just accept that it's 3/2. Energy number of moles. Now, if you notice over here, NERT, this is basically the right side of the gas law equation. It's just NERT. Okay, this is just without the PV. But the PV side gets you joules, which is why this is joules over here. Okay, so that's the correlation factor. Now, we'll talk about the negative P delta V and the significance of the negative sign in just a second. So at this point, here's what I want to do. I want to calculate the delta U for this system. So I want to have, because we know everything. We know the number of moles, we know the ideal gas law constant, we know the change in temperature. Okay, because we know the final and the initial temperature. So here's the deal. So this delta U is going to equal 3/2 that number of moles, which is 0.1, the same R, 8.314 joules per mole Kelvin, times, now, on our temperature, since the very first day you've been in this class, am I going to take temperature final minus temperature initial, or temperature initial minus temperature final? Final minus initial, just like from the very first day you were in this class. So what was that final temperature? 4330?
Yeah.
And that initial temperature was 14 what? 1443 Kelvin. Now, so I'm going to take number of moles, which is 0.1, times the gas law constant, times my final temperature of 43,330, and that initial temperature of 1443. Now, before you do any calculations, is delta U going to be a positive or negative number?
Positive.
Positive, okay? So what that means is that in this process, the overall energy of the system is going to increase, okay? Because I'm going to have a positive delta U. So what do you get for delta U?
3612.
We'll call it 3,600, okay? Joules, all right? So what that means, and this is, of all of these, delta U is the hardest one to kind of conceptualize. It's like, okay, great, we've added 3,600 joules. What does that even mean? Here's what you, for now, here's the conceptual side. All this means is that in this process, the overall sum total of all of the energy in the system is going to increase. Okay? That's all you need to know for now. When I get done, I'm going to increase the energy of the system. That's all you need to know for now. Now, let's talk about this. Work equals negative P delta V. I can also do this because I know my pressure, I know my final volume, and I know my initial volume. So when you look at this, okay, let's go back to the graph. Basically, what I'm trying to find is the area underneath this curve, okay? Because if you look at this, oh, this is a rectangle. Oh, we've talked about that before. Oh, look, it's a rectangle. It's 1.2 times 10 to the 5th meters tall. It's 0.02 meters wide. Oh, I'm finding the area. So when I find this area, I'm going to take a pressure, which is in newtons per square meter, and I'm going to multiply that by cubic meters. So what units do I get for the area underneath this line?
Joules.
Joules, because it's newton meters. So the area underneath the pressure volume graph is going to represent work. Okay? So this area is going to represent work. So this whole thing, this is what I'm going to find. Now, here's what's important. Work is going to equal negative P delta V. You'll see why this negative sign is so important. This isn't just random. It's like, why is there a random thing out there? It'll make sense why this is there in just a second. So I got a negative pressure, which is 1.2 times 10 to the 5th newtons per square meter. Now again, change in volume. It's going to be what minus what? Tori, what minus what? Final minus initial or initial minus final?
Final minus initial.
So what's my final volume, Tori?
0.02.
Nope. One more.
3.
0.03. What's my initial volume?
0.01.
There you go. Now, so, is this going to end up with a negative sign or a positive sign?
Negative.
Negative.
It's going to be a negative sign, okay? That's really importante, okay? I'm going to end up with negative work, okay? I'm going to end up with negative work, and you see the significance of this. So when you do the math, what do you get?
Negative 2400.
Negative 2,400 joules. So at this point, here's what we've got. We know delta U equals Q plus W. We calculated delta U, and that was what, 3,600 joules?
Yes.
Okay? Now, I don't know Q, because again, I don't have a Q probe. Okay? I can't directly measure Q. But I can now, but I know my work value. So that's going to be negative 2,400 joules. So, can I figure out what Q is?
Yes.
Yeah. Because what am I going to do?
Add-
Well, I'm going to add this over, and what are you going to get? Q is going to equal what?
6,000.
6,000? Now, here's the analogy that I always make, okay? When you end up with negative work, and this is understanding thermodynamics is all about understanding prepositions and understanding signs, okay? So in this situation, the volume has gotten bigger. Anytime, without fail, if you increase the volume, that means that you're going to have negative work, okay? Because it costs energy to make the volume get bigger. Because you have to work against the atmospheric pressure that's trying to hold this thing down, okay? So anytime you increase the volume, work is going to be a negative number. If the volume becomes smaller, work is going to be a positive number. So the preposition that goes with this is that we say that work is done by the system. So if you see the words by the system, okay, that means that this volume has gotten bigger. So here's the analogy that I can make. So we said that Q was going to be 6,000. So here's what's going to happen. 3,600 joules is going to equal 6,000 joules plus a negative 2,400 joules. So upon my passing, here's what's going to happen. I'm going to leave Bree $6,000. Okay? Even though she was wearing a KU shirt, I'll forgive her for that. I'm going to say, Bree, here's $6,000. Okay? So that's the amount of energy that's going to flow into the system. So into Bree's bank account, I'm going to flow into this system $6,000. Okay? And that's going to be positive because energy is flowing in. So anytime you have a positive Q, energy is flowing into the system. But here's the deal. Okay, here's the caveat. I want to go, okay, to Bree, I leave $6,000. But she has to take $2,400 of it to make the world a better place. She has to build something, okay? A pet shelter, an orphanage, something, okay? She has to do something good with the money that she has given. And she's going to build something and make something bigger. So whenever something is made bigger, the volume is getting bigger, that's going to cost Bree some of the money that I left her. Now, this is what Bree gets to keep, okay? So her overall, even though she's got to spend $2,400, she's going to get to keep $3,600 of it to increase her overall bank account. So she's going to get $6,000, nice chunk of change. She's got to spend $2,400 of it to make the world a better place. She keeps $3,600 of it, okay? Go with this. So visually what's happening with this syringe, I'm dumping in 6,000 joules of energy because Q is positive. 6,000 joules of energy is going in. 2,400 joules of that is going to make the syringe and the volume get bigger. What's left over is 3,600, and that's what's increasing the temperature of the particles. Okay? So 6,000, she's going to spend 2,400 of it. 3,600, that's what's going to buy Skittles for Timmy to turn him into dashes. We good?
Yeah. My brain is...
Oh, yeah, well, we're not even near to that point yet. Okay, we got more to go. Okay, so here's the deal. So let's go back here and let me kind of erase a lot of this. Okay, so here's what we've got. Nice little summary going across here. So this is going to be isobaric, right? So on an isobaric process, delta U is going to be a positive number because we are increasing the temperature, okay? Because we've got a positive delta T. Q is going to be a positive number because of the fact that we're dumping energy into the system, okay? So Q is going to be a positive number. Work is going to be a negative number because we're increasing the volume. So here's what's happening. Here's the syringe. I'm dumping energy into it. It's going to take some of that energy and it's going to make the volume bigger. But I've also got to take some of that energy to increase the kinetic energy so that way I can maintain the same pressure. So I'm going to split the energy. Some of it's going to go to make it bigger. Some of it's going to use to increase the kinetic energy. Now, here's how you can get a feel for this concept that expanding gases cost energy, okay, which is kind of this nebulous idea. So here's what I want you to do. Put your hand about 3 inches in front of your face and breathe on it with your mouth open, okay? So just go like this, go. Now, how does it feel?
Warm.
Amazing.
Feels warm, right? Okay, feels warm. Now, I want you to do the same thing, but I want you to pucker your lips and then blow on it.
I see what you did there.
That's a helicopter.
Now how does it feel? Cool. Ooh. So why, even though it's the exact same air, in one situation it feels hot, in the other situation it feels cool.
Pressure increase right there, Berg.
Kinda. You gotta compress it, but then as soon as it gets past your lips, what does it do?
It goes fast.
Oh, it expands. Okay, well, it also goes faster, okay? But for now, let's talk about the expansion, right? So it's going to expand. So as it expands, that costs it energy because of the fact that it has to push against the atmosphere that's trying to keep it confined. So when you do this in your pucker, okay, it feels cool because once that air gets past the compression stage, it expands. As it expands, it cools, and it cools because it's losing energy because it has to fight to expand. So this is how like your air conditioners work in your car or at your house. Okay, they work on one of the most vital things that you have in your air conditioning system is a compressor because it compresses the gas. And then you let it go through an expansion area, and then as it goes through that expansion area, it cools down because of the fact that it's occupying more space. So if you've ever had like a can of like that compressed air, okay, if you ever dealt with that, like for cleaning computers, okay, if you spray it, what happens to the can?
It's cold.
It's cold. Oh.
And you turn it upside down, and then
Yeah,
and
you
then
turn it upside down,
and
you
then
get frostbite.
and then you put it in your.
No, keep going.
What? What's up?
You showed a little bit too much
No,
information.
no. That's how you're supposed to do it. They say it on the can
What?
that you're supposed to huff it. What do you want me to do? It says do not inhale. Like, just tell me to do it.
Because it said not to, therefore you have to.
They're implied.
Yes.
It's implied.
Okay.
They're trying to pull a fast one on me, but I'm too bright for that.
You stick with that motto. You let me know how that works.
I mean, it's working pretty good right now.
Okay, all right.
Do not jump on.
Okay.
I'm gonna do
So, you're going, now, what do you think would happen if we reverse the process? If we take this at 15 and we condense that thing back down to 5, what would we have to do?
You take energy out.
Take energy out, we put it in a water bath. What would be the sign of W?
Positive.
Positive. Q is going to become,
Negative.
and delta U is going to turn negative. So if it's going in one direction and everything is positive or negative, if you reverse it, everything just switches sign. Okay? Got that?
About the expansion thing, so when
Yeah.
our mouth was open, it was already expanded, so it didn't have to
Yeah.
go through that process.
Yeah, there was no work that you went through to compress it.
Okay.
But then when you had to actually do work to compress it, okay? But then once it got past that, then it's going to expand.
Okay.
Okay? All right, Sam, shut that, or Max, shut that down. Let's stand up, take a stretch, and go. Who touched the camera?
Yeah.
Why?
It makes them mad, it's really funny.
No, it's not.
You should have seen his reaction.
No.
That was a good reaction.
Yeah. Okay. So we've gone through the most complex one. Then now it's the second most complex one, and the last one will be the easiest. Okay. So we said if it's an isobaric, this is called what we call an isobaric expansion, meaning that we have the same pressure and we're going to make the gas bigger. Now we're going to go through what's called an isothermic expansion. So isothermic means we're going to keep the same what?
Temperature.
Temperature. So we said the temperature up here at this point was 1443 Kelvin. So we're going to go from 1.2, and then we're going to go down here to 0.03. Now, here's the deal. If we're keeping the temperature constant, why does the pressure have to drop as the volume gets bigger? Think in terms of Timmins.
Is there
Because
fewer
they don't-
collisions?
Okay?
They don't have as many
No,
skills.
no, 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 no. Okay.
Collisions.
So here we are at 5, right?
Right.
Okay? We're going to go to 15, and the pressure drops.
Yeah.
So but the temperature is constant. So we still have Timmy's, right? We haven't gone to dashes yet. So why does the pressure drop when I pull that syringe back?
There are fewer collisions.
There's more space, there's going to be less collisions. So I've got the same number of Timmy's with the same amount of energy, but now it's a bigger space. So since I didn't alter the temperature, they're hitting with the same amount of kinetic energy. But as the volume gets bigger, you're going to just have fewer collisions. Okay? So it's like this. Imagine that we're going to take the hallway and we're going to double the width of the hallway, during passing periods. That would be nice. So you're going to have a fewer number of collisions. Kids are going to walk at the same speed, but you're not going to have as many collisions.
So that would change at all, or is the temperature the
No,
same?
the temperature is your measure of kinetic energy. So you all would be walking at the same speed.
Okay.
Okay? So, but we're still going to have we're going to have less pressure on the walls because we're increasing the volume. Okay? Cool with it. All right. Now, I don't have to worry about finding the temperature here because of the fact that it's isothermal. I know when I get over here, I'm still going to end up at that same temperature of 1443. So, since it's isothermal, okay, so here's what I want to look at. Delta U equals two things. It equals Q plus W, and delta U equals 3/2 NR delta T. What's going to be my value of delta U?
0.
0. Absolutely 0. Why?
Because there's no change in temperature.
There's no change in temperature in this process. It's isothermal. So since this, on isothermal, is going to equal 0, delta U then is a big goose egg. So what about Q plus W?
It's got to be 0.
It's got to be 0. So that means that my Q and my W have to be
Equal
and opposite.
equal and opposite. So what that means is this. If you go with the analogy, I'm going to leave Bree a certain amount of money, $3 grand, whatever it is. But she doesn't get to keep any of it. So I'm going to say, I want to leave you $3 grand, but she has to spend all of that money to make the world a better place. Okay? Right? She doesn't get to keep any money at all. She has to spend it. So her bank account will not increase in the least. Whatever money goes in, she has to use to make the world a better place. Okay? And don't give me a frowny face on that. Okay? You get to make the world a better place. You'll feel good
Does
about it.
that go to my student loans?
If that makes the world a better place, yeah.
Yeah.
Okay.
Um,
All right.
service.
All right. So delta U Q plus W. Now here's the question. Could I use negative P delta V for this calculation on an isothermal expansion? So could I use work equals negative P delta V to calculate this area? You shake your head no. Why, Ethan?
The pressure is constant.
Oh, you don't have a negative change.
Pressure.
Well, yeah, I don't have a constant pressure, right? If you try and use work equals negative P delta V, I do have a change in volume, I'll give you that. But I don't know what pressure to use, because the pressure is always changing, okay? And here's what's going to be important. Geometrically, this is a curved line. This is not a straight line. Now, here's the reason why this is a curved line. The reason it's a curved line is because you have PV equals nRT. On this expansion, what's happening to NERT? What's happening to this side of the equation?
It's 0.
Absolutely nothing, right? This side is staying the same because it's the same temperature, it's the same number of moles, it's the same arc. This side of the equation isn't changing. Well, look, so if this side isn't changing and my volume is getting bigger, what has to happen to my pressure? It has to get smaller. So it's like an inverse relationship. As volume gets bigger, pressure has to become smaller and smaller and smaller. And that's why this is a curved line, okay? Because of the fact that it's an inverse relationship between pressure and volume. Okay. Now, what I've got for this particular situation, and I can't use this because work equals negative P delta V. So because of the fact that it's a curved line and you're finding the area, you actually have to take the integral of the equation of the line, okay? And it's a calculus thing, and you're finding the area underneath the curve. So this is like a real application of calculus. But what you've got is nRT, natural log of volume initial over volume final. Now, I've got everything that I need to do this. So here's what's important. I can only use this if I have a constant temperature. So I couldn't use this on that isobaric expansion because the temperature was changing. Just like I can't use this on an isothermal because the pressure is changing. So you have to realize, oh, what am I going to use in different parts of this equation? Okay, so don't do any math at all. Nobody breathe on a calculator for now. Mary, don't even breathe on a calculator. What did it take? Don't breathe on it. What did you do? Breathe on it. Okay. So I got 0.1 moles. I've got my R value, which is the same thing, 8.314 joules per mole Kelvin. I've got my temperature. What's the temperature? 1443? Okay. And then I've got a natural log of, and I'm just going to write this up here, volume initial, which is 0.01, and then the volume final is 0.03. Now, don't even breathe on a calculator. Don't even breathe on a calculator. So there's a couple of cool things that when you do natural logs, and this only works with natural logs. When you take the natural log of something, the cubic meters drop out. Okay, when you take the natural log, what you end up with has no units. It's the only mathematical operation that really happens with this. Okay, this has no units. Once you take the natural log, the units are wiped out. And you studied like advanced chemistry, you'll see that as well. Natural logs wipe out the units. Now, but what happens is I've got moles times joules per mole Kelvin times Kelvin. So this whole thing gets me joules here. So don't look at this and go, oh, I have the natural log of cubic meters left over as units, which doesn't have any meaning at all. So this has no meaning. So this has no units. It drops out. Now, for those of you that have studied natural logs, which I'm guessing the vast majority of you. So basically, this simplifies down to a third. I'm taking the natural log of 1/3. So quick refresher from your natural log studies. If you take the natural log of a number that is less than 1, is your natural log a positive or negative value? Negative. So guess what the side of my work's going to be? Negative. Oh, that fits because of the fact that I'm making the volume bigger. So I should end up with negative work. Okay? So that's how this fits into one big idea. Now again, don't touch a calculator, do not touch a calculator, do not touch a calculator. So this work up here, what was the work up here? Negative 2400?
I can't touch my
No. From when we did the isobaric. Was that work negative 2400?
Yes.
I think so.
Yes, it was.
That's I think that's right.
Because the other thing was
Yeah, it was
3600 and it made 60.
Negative 2400 joules. Yeah. Now, this is why I don't want you to touch a calculator yet. When I find this area under here, is that answer going to be bigger or smaller than negative 2400?
Smaller.
Mary,
Smaller,
why?
because it'll be like half as much.
Yeah. This is a smaller area. Okay? This is a smaller area. So what that means is an isothermal expansion is less work than an isobaric because of the fact that you're going to have a smaller area underneath this curve. So just looking at this, you can look at this and go, oh, right, okay, should end up with a smaller value, but it's still going to be negative, okay? Now, we can punch the numbers. So it's going to take 0.1 times 8.314 times 1443 times the natural log of 130.
Negative 1,400.
So you get what?
Negative 1,318.
Joules. So that kind of matches with what we said was going to happen, right? Mary said, oh, it should be about half, and it kind of is, right? That was negative 2400, this is about negative 1300, pretty close to about a half, okay? So what this means is that now I've got my work value. So here's the big kicker, and this is where this all comes together. we said delta U equals Q plus W. Delta U equals what?
0.
0, because there's no change in temperature. Now, what was my W value?
Negative 1300.
Negative 1300?
Yeah.
So, how much energy did I dump into the system? 1,300 joules. So what this means is that upon my passing, Bree gets $1,300. But she doesn't get to keep any of it. She has to spend it to make the world a better place, even if it's reducing her student loan debt. Okay? Because that'll make the world a better place somehow. Okay?
Yeah.
Right? So, if its delta U is 0, that doesn't mean we're not doing stuff. Okay? What that just means is that your overall internal energy is 0. So, what would happen physically, what you would see in this situation, is that you would have a syringe with a certain volume. You would dump it into a hot water bath because you have to dump energy into the system because I've got a positive Q. I'm going to dump energy in, and what you would see is that gas expands, and you would see that syringe get bigger. So the only way this works is if your container can change volume. If this is a rigid container, like a sealed can of pop, you can't do this because there's no change in volume. Okay? Huh?
Isn't that why they explode like when they get
Yes, because then the pressure goes up too high. And, okay? Yeah. Okay. Got this? No. So as a quick summary, Matt.
So what about the cans exploding in the freezer?
That's just because ice occupies more space.
Okay.
That's because you're forming ice is less dense than liquid water, and that's because of the formation of ice. Okay, which is also why your engine blocks will crack if you let water freeze around your engine.
Yeah.
Because that ice expands. Okay. So here's what we've got. On an isothermal expansion, we're going from here. So on this one, we'll delta U is going to equal what? On an isothermal expansion, delta U is going to equal 0. Q is going to be a positive number, which means that we're going to dump energy into the system. And W is going to be a negative number because volume increased. Okay? Work is done by the system. Now, if you reverse this process, we would say that work is done on the system. So in that case, if you reverse this, what I would do is I would take this and I would seal it up and I would compress it, but that energy is going to flow out of the system. So like this system, like I can't do this like in an insulated container, like any of your drink containers. I can't do this because what's the purpose of an insulated container? Yeah, you prevent a thermal loss. You prevent the flow of thermal energy across a gradient. So this can't happen on an insulated system because you can't allow that energy to flow in or out. Okay? So that's also kind of what you need to look at. All right, so it's the only thing we have left. Hunter.
In isothermal, will
Yep.
the change in temperature always be 0?
Yes, that's by definition, is that you're keeping a constant temperature. By definition, that's what that means. Okay? All right, so we got one thing left to do. And that is isometric, sometimes it's called isovolumetric. So visualize this. Okay, we're here, we'll keep the same numbers. 5th, and we're out here at 0.03. And so at this point out here, we're at 1.2 times 10 to the 5th newtons per square meter, and okay. So here's my data point. I'm at 0.03 cubic meters, and I got a pressure of 1.2 times 10 to the 5th. So what I'm going to do is I'm going to take this line, and I'm going to bring it down here to 1.0 times 10 to the 5th. So we're gonna go from here straight down. And I'm gonna end up at 0.03 cubic meters and a pressure of 1.0 times 10 to the 5th newtons per square meter. Now, think this through. Okay? At this point, you should be able to visualize what's happening. So, is the volume changing?
No.
Not changing. So, what's my work going to be?
0.
Why?
Zero slope.
You're not changing
No. What? Okay, number one, I'm not changing
volume.
volume. And what's the area underneath the line?
Nothing.
Nothing. There is no area to calculate. So, how much work is done?
0.
0. Okay? So what that means is that what I would have to do is lock this syringe in place so it couldn't move. Okay? That's what I'd have to do. I'd have to lock this syringe in place so there could be no movement. It's just going to be locked in place. Okay? So there's no movement. So this would be like a can kind of deal. Now, think about this. I'm going to bring this line straight down. Pressure is decreasing. So before you do any calculations at all, is the temperature down here going to be bigger or smaller than the temperature up there?
Smaller.
Smaller. Why? There's less pressure. I didn't change the size of the classroom, did I? Didn't change the size of the classroom. So what's the only way, since I'm not changing the size of the classrooms and I'm not changing the number of Timmies, what am I doing? Yeah, I'm taking Skittles away from Timmy, right? I'm making Timmy chill out. So Timmy's on this post-sugar high at this point. He's going, oh, it's nap time.
He's gonna crash.
He's going to crash.
That's right.
Yeah. So we went from Timmy to Dash to Crash. Okay? So we got Timmy here, we got Dash here, we got Crash here.
I like that.
Okay. So Timmy, Dash, Crash. All right. I like that. Good. So can we find the temperature of Crash?
Yeah, probably.
Yeah, we have a pressure, we got a volume, and we got the number of moles. So all day long we can go, oh, PV over NR is going to equal our temperature. So I got a pressure of 1.0 times 10 to the 5th. I got a volume of 0.03 cubic meters. I got moles of 0.1. And I got an R of 8.314 joules per mole Kelvin. So some take 1.0 basically times 10 to the 6 times 0.03 divided by 8.314. What do you get? It's got to be less than 4,000. Mary? I'm just going to go straight to the source.
3608.
3608.
Mary?
3608.
Okay, love one calculator's good. So we're at about 3,600 Kelvin, right? So we were up here at, what was this temperature up here, 4,300? Okay? All right, so we dropped some temperature. So, what does delta U also equal? Q plus W, it also equals, so let's look at this. So let's kind of start over. So, delta U equals Q plus W. In this situation, what's my work value? 0. Why?
No area.
No work involved. Okay? This is a freshman gig. I get no work. Okay? So, Q, I don't know that because I can't directly measure Q. I don't know what Q is at this point. But I can find delta U all day long by going 3/2 NR delta T. Now, again, before you touch a calculator, is delta U going to be a positive or negative number?
Negative.
Negative. Why?
There's
You went from dash to crash.
Temperature goes down.
Temperature is going to go down, right? We went from dash to crash. So, I got 3/2 0.100 moles. I got an R of 8.314. And then my final temperature was, what was the final temperature? What was that number we just calculated?
3600.
Huh?
3600.
3,600. And then initial temperature was 4,300. So do the math. Take 3/2 times 0.1 times 8.314 times 3,600 minus 4,300.
Negative 873.
Negative what?
873.
So negative 808. So here's the deal. To make this happen, what would you do? To physically make this happen, what would you do to this syringe?
The change was 873, not 8,073. The change was 873, not 8,073.
I got negative 400.
Whoa! So you got 3/2 times 0.1 times 8.314 times 3,600 minus 4,300.
Yeah, and I got negative 873.
873, not 8,073.
What are y'all doing?
Yep, that's right. Yeah.
Negative what?
873.
873.
Should have just asked me. So, okay, now that we've got that resolved again. What would you do to this syringe to make this deal happen? What would you do?
Put in an ice bath.
Put it in an ice bath, right? But you'd have to lock up the cylinder so that it couldn't move. Okay? So if you go back to this, so going from here to here, what's work going to equal?
0.
Because it has no volume. Okay? So the beauty of this is Bree doesn't have to do any work. Okay? This is no work at all. So delta U, though, is going to equal a negative number. So Q is going to equal a negative number because we're going to dump energy out of the system. So in other words, Bree, I'm going to go to Bree and go, hey, Bree, what is that? Sorry, my bad. I didn't die after all. Okay. But if you reverse it, if you're here and you wanted to go up there, what would you do? You'd dump energy into the system.
Positive.
Yeah, then you'd have a positive U and you'd have, because the temperature would go up. Okay? So again, this is a situation where I can't directly measure delta U, but I can put a temperature probe in here all day long and measure what happens to the temperature. Once I get the temperature and I measure that change and I know that volume isn't changing, this situation is the easiest. This is why I saved this for last, because this is the easiest because you just have to worry about delta U and Q. So this is a situation like you have a sealed container like a can of pop. So especially if you start here like on a warm day and you warm up that can of pop and that volume can't change, what's going to happen to the pressure inside that can of pop? It's going to increase because there's no way for it to go, okay? Because you can't change the volume.
So why does Mentos increase the pressure of pop?
Well, that's a chemical reaction that just releases a lot of gas. That's why. Okay, cool with that. All right, stop that. Okay, so number one is actually a true story. So when I wrote this problem, I was actually eating an almond joy. So here's the deal. Let me kind of give you a brief history on food calories. So by definition, a calorie with lowercase c is the amount of energy it takes to raise 1 gram of water 1 degree Celsius. Okay, and that's 4.186 joules. So, if in biology, did y'all do the lab where you like took like a Dorito chip and you burned it and you measured the change in temperature of water, and it was calories, okay? And so y'all just accepted it. Well, this is the basis of this equation because that energy went in to warm up the water, and then however much it warms up the water, that's theoretically how much energy was in the chip when you burned it. That's the basic idea, okay? But here's the problem, is that when they actually started doing the analysis, especially like on almond joys, and if you use the lowercase true definition of a calorie, you would have like 230,000 calories by true definition of a calorie in an almond joy. And the people are flipping out going, we cannot have people thinking they're consuming 230,000 calories. Sales are going to plummet. So they got clever and they said, okay, let's just lop off the last 3 zeros, okay? But then we're going to have uppercase C. So this is why up here on this conversion I have 1 uppercase C calorie is equal to a kilocalorie, which is 4,186 joules. So they figured, hey, if they see 230 joules, they could probably live with that. If you say, oh, you're consuming 230,000 joule or calories, oh my God, there would be a train wreck. So basically, you lop off the 3 zeros on the end, and that's what a food calorie is. So there's a food calorie, and then there's like a physics calorie. And then we switch over to joules, so it doesn't matter anyway. So here's the deal. You consume a Snicker or an Almond Joy, it's got 230 calories. Out of that 230 calories, you can functionally use 25% of it. Okay, so that's about how efficient we are. Same thing as like your gasoline engine in your car. They're about 25% efficient. So when you buy 100 joules worth of energy for your car, you only get 25 of it that you can actually use. So that's going to be the basis of this. Now, on some of these, you're going to have to draw like a sketch of a position volume graph. It doesn't have to be on graph paper, but if you do it on your paper, draw it big enough that where I can see it so I don't have to guess what the numbers are. Okay? All right, I'm done. You're on your own.